Okay, so today I'm going to talk about p-adic families of Yoshida leaves.
Yeah, looks good.
Okay, so I hear some echoes here. Is there? Do you hear me clearly? Okay, so I'm going to start with some introduction and motivation. So I'm going to start with two capital lambda-dic families on GL2 at F and G underline. So the lambda here is the usual Iwasawa algebra, ZP double bracket. So for simplicity, I'm going to just use this lambda instead of more generally maybe a finite extension of the lambda. I will then these two Hida families is going to give us two lambda-dic eigensystem. I call it lambda sub f and lambda sub g. And then they are going to give us two lambda-dic Galois representations. Call it rho sub f and rho sub g. I'm going to assume that the determinant of this rho f and rho g inverse, it has a square root inside the tensor product. Hello?
No, you might
Yes.
have two devices at your end, which is creating some echo.
Right. Let me try to.
I speak, there is no echo. When you speak, there is a bit of an echo.
Yes, I need to kind of stop the audio from my iPad, but seems like I had some issue to figure it out. So give me a minute. Let me try to see.
Okay, so why is this happening? Is this happening just because?
This was better.
It's not bad.
No. Again, echo.
Yeah, yes, I know.
So this is happening is because when we put x equal to 0,
Okay. I guess maybe I have to maybe stop my audio.
Madam, there is the more option is there in the downstairs.
The more option?
Yeah, more option.
Yes, here.
Yeah. Yeah, disconnect audio.
Oh, yeah, okay. I found it. Okay, great. Thank you. Yeah, it's I think it's the Zoom has made some changes. Okay, so let me go back. Okay, thank you. Okay, so I will assume that the determinant rho f and the determinant rho g inverse, it has a square root inside the ring lambda tensor lambda. I call it lambda 2, so it's going to be a two variable Iwasawa algebra. And then I will consider a lambda 2-adic Galois representation, which is basically you just direct sum these two Galois representations, and this will be a reducible representation, and this also will correspond to lambda 2-adic Hague eigensystem for GSP4. And we can view this as a Yoshida lift of the hierarchical system of the Hida families F bar and the G bar. And by the theory of the theta correspondence or the Yoshida lifts, we know that actually this lambda 2 eigensystem will show up in the Hecke algebra for the ordinary Hida families on GSP4. And so we have this Hecke eigensystem. We can consider the congruence ideal associated to it. So if I have the ordinary Hecke algebra on GSP4 with a suitable time level, and so I can map it to a tensor with a fraction field of lambda 2, and then it will decompose. It can decompose into a component which corresponds to the Hecke eigensystem given by this Yoshida lift. And there is also a remaining part. And I will define the congruence ideal as the following. So I have this to be the image of this.
Can you try to make it bigger?
Oh, yes, sure. I will do maybe I can just. Is this good? Okay, so the image of this, of the kernel of mu under this lambda f sub fg, and this will be inside lambda 2, and this will be the congruence ideal. For the Yoshida lifts. And we know that because we have a reducible a representation here, if we consider the congruence with the other Hecke eigensystem showing up for GSP4 by using Ribas lemma, we can produce a lower bound for the size of the Selmer group for rho F tensor rho G. And actually, this part has been studied by Mingwen Xie and Bharat Pavanan. And today I'm gonna talk about more about how to studying this congruence ideal on the automorphic side. And so in order to study this, we have one strategy is to follow actually the strategy in the work by Hida and Chiloing actually when Jack already explained in his lecture. So let me recall this type of strategy. So the strategy is kind of we just cook up some integral family on ordinary family on GSP4. And then we consider the projection to the head eigenspace corresponding to the lambda Fg. And then we'll apply it to this integral family curly G. And then if we can write it as something divided by an element in lambda 2. So anyway, so if this applied to this curly G gives us some form F over an element L. So where F is an integral Hida family, or not Hida, maybe say ordinary family. On GSP4 with some Fourier coefficient being a unit. And we have also this L on the denominator, an element in L2, lambda 2. Then we can conclude that the congruence ideal is contained in this denominator, because if we apply any element in the congruence ideal to this, we should get something integral. So you should cancel the denominator. And so actually here I'm requiring a stronger condition here that this the form on the numerator actually has a Fourier coefficient in lambda 2 cross. So it's a bit different from what explained in Jack's lectures, where they can kind of have some clever argument to show that basically what they want is some co-prime of the numerator and the denominator. And somehow this is the strategy of Hida Thiele's work. And so this whole thing maybe can be viewed as a generalization of their work, because they were considering congruence of the CM with CM forms, which kind of theta lived from O2 to GL2. And here we're kind of considering the theta lived from O4 to SP4. And in that case, in their case, this what they put this G is a CM form multiply the product of the ordinary projection of a CM form, product of CM form and Eisenstein series. And in our case, we're gonna actually choose certain Eisenstein series to place this role of this curly G here. Okay, so before to state the result, I want to mention some previous work in this direction. Actually, so for previously there's some work where they consider the instead of consider families, they consider some fixed f and g and consider this trying to do this congruence. Okay, so let me try to. So at the, there is the work of Jia. So he was considering the modulo p now vanishing of the Yoshida leaves of f and g when properly normalized. So basically, he was considering that's correspond to in the end to considering some this numerator, the form on the numerator to be have a free coefficient to be a unit. And there are also works by Barker, Dominion, and Schulz, Pillard, and Arguer Clausing. And in their work, they use this G, the curly G, to be the restriction of Ziegel Eisenstein series on GSP8. And all these works are kind of, they are under some very strong assumptions. And so, so for example, in this work, when they use this Ziegel Eisenstein series from GSP8, so actually they have to kind of assume that the when there is a p divides the denominator, and then that will not divide the numerator instead of directly proving that the numerator is a unit. And then there are also the work by Shien and Namikawa also. What they did actually is they proved kind of a non-vanishing of non-vanishing of this Yoshida leaves under a reasonable condition, and also they computed the numerator. So maybe I should write here. So why they compute this this Peterson inner product is because we know that heuristically, if I look at this projection, so let me write here. This should be the inner Peterson inner product of this G. If we have a family of Yoshida leaves as families, then this should be equal to the Peterson inner product with that divided by the Peterson inner product, the Peterson norm of this Yoshida family as the actual family of automorphic forms. And then we have this, or yeah, I can put this on the numerator. So basically what we want is to show that we want to know about the denominator, and also want to show that the numerator is a unit. And okay, so this is the previous work. So next, let me just state what the main result I want to discuss today. So this is a joint work with Minglun Xie. Okay, so actually I already pre-wrote some conditions of the, I guess I have to make it larger. Okay, so Make it larger. Okay, so I will just put everything to 2 lines and then resize it. Okay. So I will given these two families F and G and of a time level gamma 0 n. And I will suppose some conditions. So I will suppose that their residual conditions are absolutely reducible. And I can write the level as n plus times n minus, where the n minus part has odd number of prime factors. And for any prime dividing n minus, both n, f, g are new at this Q. And also I want to assume this level is square free. So basically at Q dividing n minus f and g are both Stenberg. And then for Q divide any of the conductor, the level n, and where both of them are new, I want to assume that they have the local sign are equal. So these are the conditions. And then I will state the result. So first, I want to say, so if we look at here, actually, in order to write this projection in terms of something, a form on the numerator and another elements in the lambda 2 in the denominator. So first, I need to actually construct this Yoshida leaves as a family of automorphic forms. So the first result will be constructing this family, and also because I want the numerator to be kind of a primitive, having a unit Fourier coefficient, also I need to make sure that this family has a Fourier coefficient being a unit. So that will be the first result I want to say here. So there exists a Hida family. Which is inside the eigenspace for the Yoshida leaf. So inside. And having a Fourier coefficient in the unit of lambda 2. And the second part, if we look at what the projection looks like, and in the end, we want to show that this L on the numerator is actually a Rankin-Selberg two variable Rankin-Selberg p-adic function for f and g. So that means I need to evaluate this Peterson norm here. So the second part will be about this. It says that if I look at the classical specializations, so for classical point, x, y, such that the weight of the specialization of f at x is larger or equal to the weight of the G at Y larger or equal to 2, and they are of the same parity. Then I have this family evaluated XY. Is given by the ranking suburb L function valued at 1. Here I put 1/2 at the center. And I use approximation sign here just to indicate there is actually some factors like a modification of P. And then so this is about the denominator, and then I will say about the choice of this curly G here, and also control of this part. So there exists a Klingon Eisenstein family. I call it curly E of H and eta K. So here H is will be chosen to be a CN form on GL2, and eta K will be a character of an imaginary quadratic field. There is such a Hida family such that you can place the role of that curly G. So this is, sorry, I should say where is this Klingon Eisenstein family is actually on GU22. And then I can restrict it back to GSP4 to get a family there, GSP4. Also, I want to apply an ordinary projection. So it's gonna be an ordinary family. And okay, then this will be equal to a Hida family with a Fourier coefficient in lambda 2 cross, then divided by the ranking suburb, the two variable p-adic ranking suburb L function for f and g, which interpolates L values at 1. Okay, so basically is combining with 1, we know that in order to make sure the numerator has a unit Fourier coefficient, we need to study is this Peterson inner product to make sure this actually is a unit. Okay. And if we combine, if we have all this, then we know by the strategy, we will be able to deduce that the congruence ideal we defined at the beginning actually is contained inside this two variable p-adic ranking Selmer L function. Okay, so this is the result. And any question? So next I'm gonna give a sketch of the proof. Okay, so again, I need to put things a bit larger. So the proof, actually, we're gonna use the, so first we're gonna try to construct this family theta f g as a family of automorphic forms. And so we need to recall some theta correspondence here. So I will let D be a quaternion algebra ramified at primes dividing a minus and infinity. And then for this quaternion algebra, I will associate a orthogonal group to it, which is I call it O4. And we know that this orthogonal group has a close relation with the two copies of the D cross. And then I will let F upper D and G upper D being the Jagiellonian transfer of the Hida family F bar G, F and G on GL2 to this D cross. And so then essentially this pair is going to give me an automorphic form here, essentially on this O4. And then I can theta lift this form on O4 to SP form. And so now we want to construct the Yoshida leaves. Basically, is to construct a lambda to p-adic family of these theta leaves from O4 to SP4 for this pair F upper D and G upper D. So to construct Hida families of Yoshida leaves, what we want is to kind of first construct a Hida family, sorry, not Hida, p-adic family of theta series, and then we want them pair with this F upper D and G upper D on O4. So to get the family of theta series for each finite order character, so chi1, chi2, basically these are the points in the weight two variable weight space, which are finite order characters. I will pick a Schwartz function, a phi sub chi1, chi2 on the two copies of this quaternion algebra at the finite points of dells, and I will always pick the Schwartz function at infinity to be the standard Gaussian function. And then I consider this theta series associated to this Schwartz function. And to construct a family, so what I'm going to do is to try to construct a family of Q expansions and then apply ordinary projector, then to say, okay, that's the actually a Hida family. And so that means I want to compute the Fourier expansion of this theta series, which is actually pretty easy to compute. So I will take a beta from the non-degenerate semi-positive definite elements in a symmetric 2x2 matrix with coefficients in Q. So these are kind of indices for a coefficients on GSP4. And I consider the beta's coefficient of this theta series valued. So this theta series is a automorphic form on SP4 cross O4. So I will value it at a point on O4, then this will be a automorphic form on SP4, and then I take the beta for a coefficients. And it can be easily computed that basically it's a finite sum of this chosen Schwarz function at a times x for finite many x. So it's a finite sum. And in order to get a family of Q expansions, I just need to make sure that I can periodically interpolate this element. So what we need is to construct a Hida family. SP4, so what we just need to make sure we need to pick this collection of 5 Chi1, Chi2 such that each of this value can be periodically interpolated. So for all x and the elements in O4. And this actually is a kind of a very mild condition. So for example, you can just pick a function that is constant, and then certainly will be, you can periodically interpolate it, and then you will be able to get a family of Q expansions. And then once we can do this, and once we have this, then we know that we will be able to get, I call this family of Schwarz functions phi underline, and then this will be a lambda 2-adic family on O4 with values in Q expansions of GSP4. And then I will just pair these Q expansion valued family on O4 with the given pair F and G upper D. Because this O4 is definite, so therefore actually there is a well-developed theory of taking the Peterson inner product for families. So I can have the O4. And once I do this, then this will give me a lambda 2-adic family of Q expansions of GSP4. And then I just apply the ordinary projector to it. And then by Hida theory, we'll know that this actually because at the every classical specializations, actually this is the Q expansion of an ordinary automorphic form. So actually we know that this family of Q expansions will come from a Hida family, and this will be our Hida family of Yoshida leaves. Okay, so this is kind of how we can construct such a Hida family of Yoshida leaves. And of course, in order to verify all those properties we need for our purpose, actually we need to kind of pick some nice collections of this phi sub chi1 chi2 so that we can do some computation to verify those properties. So let me see next. So we need to do many computations to verify what we want. Okay, so let me recall what we want to prove for this family. So first property is we want to show that there is a Fourier coefficient, which is a unit. And what we're going to do is we want to compute the Bessel period of this family, because we know that the Bessel period is gonna be a linear combination of the Fourier coefficients. And also we have the result about the Bessel period. We know that actually this should give us some central value of f and g twist by some imaginary characters of imaginary quadratic field. So we know heuristically what should get from this. So this will be so for some finite other character imaginary quadratic field. And then for this, we can use the mod p non-vanishing result to pick a good eta k, so that this will give us a unit. And for the second part is we want to know actually the numerator, this Peterson norm of the Yoshida leaves. And that will means we need to compute. This will be computed. We can compute this by using the Raleigh's inner product formula. And so this, we know that heuristically this should give us exactly what we want, the Rankin-Selberg L function at value at 1. And the last part is to compute the Peterson inner product of our construct family with this restriction of Klinger-Eisenstein family. And this actually is by the Furusawa's formula. We know that this should give us, we can arrange that that's going to give us the central value of the L function for F, the Rankin-Selberg for F, and H, then times the Rankin-Selberg L function of H and G. So here the H is the CM form. And we pick suitable CM form, this H, to make sure that we can get the unit. And so that's the computation we need to do. And so in particular, we need to do this computation at P, and our choice of the Schwartz function actually need to make sure that it will be convenient for such computations and also will give us the desired result. So actually here, our criterion for picking those Schwartz function is not only we want those values can be periodically interpolated, actually, maybe more importantly, it's convenient for us to do these computations to verify what we want. Okay, so next I'm gonna say our choice for this Schwartz function, in particular the one at P. So actually what we're gonna do is we're gonna put for choice away from P, we're gonna put a constant independent of chi1 and chi2. And actually those choices actually already in particular for these two, the first two computations, they were already made in the work by Shi and Namikawa. We're gonna just use those ones. They are constant independent of chi1 and chi2. And now I'm gonna say what we're gonna put at P. So a good choice. So I will first fix an isomorphism of the quaternion algebra at P with the four-dimensional space equipped with this standard split orthogonal form. And then I will write elements in D of QP as the 4x2 matrices with elements in entries in QP. So I will pick this one, which is I1, I2, 1/2, x1, I2, inverse 1/2. Of the determinant of the upper 2x2 block. And then times the characteristic function of the set of the integral elements here. And so here I require these two characters actually to take value 0 outside ZP cross. So they are characters of ZP cross, and extend them by taking value 0 outside the p cross. And so this will be the choice we make. If you have seen some constructions of Eisenstein measures for constructing some p-adic functions, you can see some similarity here, that you want this upper left element to be inside ZP cross, and then the 2x2 block to be inside GL2ZP, and you put the characters there. So there is some similarity there. And so this is going to be our choice. And what is the good property of this choice? The good property of this choice is that this section actually has a UP equivalence property. So meaning that if I apply the UP operators, so this is I can act this stress function can be acted on by both elements inside SP4 and O4, and so I can consider the UP operators from SP4 and the UP operators from O4, and under these actions it has an equivalence property. So if I act by the UP operator from SP4, and this will be actually equal to a scalar then times the UP operator from O4 acting on it. So these two are the UP operators for this diagonal matrix p to the a1, p to the a2, p to the negative a1, p to the negative a2. So this is an element in both O4 and SP4. And O4, and here I have a1 larger or equal to a2 larger or equal to 0. And so this scalar is actually independent of chi1, chi2, and can be arranged to be a unit under suitable normalization. Okay, so this is a good property in the sense that once we have this UP equivalence, if we look at the family we constructed before, this one, so then in particular, then with this choice, we don't need to apply this ordinary projection. Will be equal to the inner product itself. This is because this p-adic, this Peterson inner product from families will have some UP equivalence property. So therefore, because this part will by this projection will be the ordinary on the orthogonal side, and because the section is picked with this UP equivalence property, it will be automatically ordinary for the symplectic side. And so that means at least when I need to do all these computations, I don't need to consider all these ordinary projectors. This actually already will simplify a lot of these computations. So this is already an advantage. And so this is this one probably, and with this choice, I can actually And also the shape is also very convenient to directly verify following the method of Shi and Naimikawa to verify that the Bessel period is there is a unit Bessel period. And okay, so seems I don't have much time. Then maybe I will just skip some details about 2 and 3. So 2 and 3 this choice also kind of convenient, and so we can do this 2 and 3 by direct computation. But actually for 2 and 3, the computation for 2 actually is easy when we assume that the Neben-Typers of F and G at P is trivial, and we can do general weight. And but for 3, it's a little bit opposite, that we need to we can now do direct computation only gives us the scalar weight, and for the Yoshida leaves, but we can do general Neben-Typers. So they're kind of complementary to each other. That actually makes verifying studying this ratio here, to studying this ratio to show that this ratio is actually some p-adic function, some L value divided some p-adic function, actually makes it a bit more complicated, because we cannot directly compare them, because you only have results, some for trivial Neben-Typers, some for scalar weights, so they don't have a intersection of infinite many points there. So this will be done actually by direct computation, then plus a trick by using another p-adic L function for the standard L representation, standard L function for SP form. So plus use p standard p-adic L function for SP form. To avoid some relatively more difficult computation for non-trivial Neben-Typers, and 3 for general vector weights. Okay, so then this will be kind of maybe pretty sketch of the proof. So I just mainly talked about the choice of a nice Schwartz function, which has the equivariance under the UP operators. And so maybe I will finally make one more remark about this choice of this Schwartz function at P for doing this kind of theta correspondence or theta lift. This is a choice for the SP4 cross O4. Actually, we can, this type of Schwartz functions actually generate to more general cases. With this UP equivalence property, actually, we have it for more general cases. For the more general cases, we can do something. We can do something similar. For in general, if we consider the SP 2n and O2m, where it's n larger or equal to m, and the split at P, and then we can consider a Schwartz function with this similar shape. And here again, here I require these characters kind of takes value 0 outside Lippy cross. And then I can consider the UP operators given a and multiples of decreasing integers. I have the corresponding UP operators, and this again, if we do the UP operators acting from both the symplectic and orthogonal groups, and again, this Schwartz functions actually has this equivariance property. And also, this is true for the picture for the symplectic and orthogonal theta correspondence. It's also actually for unitary and unitary. We'll have a if we consider a similar shape of Schwartz functions at P, will also have this equivariance property for UP operators. Okay, I'm gonna stop here. Thanks for your attention.
Hello, this is Jacques.
Hi.
So how do you define the Peterson product for two Hida families on SP4?
Actually, it's I never defined the Peterson inner product on SP4. What I did is actually just to do this Heck projector. On this side is actually just a heuristic, so this is it's not something I really define, but what I have is to do the evaluations of this right hand side on classical points. So basically, this is saying that when evaluated at classical points of the left hand side is equal to the Peterson inner product at the classical points on the right hand side with the modification at P.
So when you say that you define your Yoshida Lift family theta FG as a Peterson product on O4, it's actually an interpolation of the Peterson product?
Yes, O4 because it's a compact, so there is a well-defined Peterson inner product also with the modification at P.
Okay.
Yeah, this can be defined for families and interpolating the standard, the classical Peterson inner product with the modification at P.
Okay, thank you. Okay.
Hi, this is Eric.
Hi.
For the generalization to ON and SP2N, O2N, so the orthogonal group is also definite, I suppose? Or can you consider?
So actually this, I'm just stating this for local at P. So I want at P, the orthogonal to be also split. So it's only about local. But if you want to do, say, theta lift families on O2M, then I think with current technique already in hand, probably if you assume it's a compact affinity, is more straightforward. But for this
Do you have
remark,
certain
it's
applications
only
in
local.
mind?
I don't have an immediate application for using this lift, but with this we can directly define a family of theta lifts for families on compact orthogonal group. But how to use that, I don't immediately have immediate application to use that family right now.
Okay. And so last question. So you explain how to get a lower bound for the congruence ideal. Do you have any idea for the an upper bound?
The upper bound, as
I mean, without using main conjecture.
for the upper bound without using main conjecture. So for the upper bound, actually, it's a Rankin-Selberg case, and unfortunately, I think it's not. We cannot directly deduce it from the Euler system because they have an assumption that actually exactly in our situation is not satisfied. So the hope is maybe from the older system, but it's not. We cannot immediately deduce it from the result we have from the older system.
Yeah, I was asking the question because if you have an upper bound, you can construct an Euler system using congruences. You already use an.
Oh yeah. So for the current, for the you're saying from upper bound to construct older system. No, we.
I mean, anticyclotomic Euler system by twisting by taking G to be a family of same. But anyway.
Okay, so twist one G to be a CM. So okay, so are you saying that if we can get the upper bound, then we can, when taking G to be a CM, we can construct the Euler system.
Yes.
Oh, okay, so I see. So, but no, we haven't. So for the congruence idea, we haven't really thought about the upper bound.
Thank you.
Anybody else? Working. This is working for sure. Hello.
Hi.
Hi, Zheng, Bharat here. I just wanted to know if you were also able to get Hida families of stable Yoshida lifts involving automorphic inductions from Hida families over real quadratic fields.
Real quadratic field. Yes, I think the method to construct the family, they should also work for to lift the Hilbert monoform of a real quadratic field. I think it's for that part, if you replace this by stable Yoshida lift, I think the 2 and 3 still works. Okay, so 3 maybe also needs to be, yeah, 3 will also be to get this part will be modified, but so all the computation of 1, 2, 3 still works, and you can construct it. The computation still works, but in the end, if you for conjuring these values for the to show the multiple non-vanishing results, those are not currently available.
I see. I had one more question. So in this method of Hida and Levine, in the CM case, they have this fudge factors involving the class group of the imaginary quadratic field. And I guess in this case, it must be like the congruences involving the Hida families, F bar with other Hida families, and G bar with other Hida families. Would those congruence numbers involving the Hida families F and G also appear in your formula?
Actually, yes. Actually, that's something I didn't write it explicitly here. So actually, so in the end, in the formulas, you will all these formulas actually you will see the Peterson inner product of the forms on the F and G on the quaternion algebra, and those Peterson norms of those, then those will correspond to the congruences with other Peters Yoshida lift. So that means what we have for our this congruence ideal here actually is a congruence with all other forms. So you will include congruence with other Yoshida lifts, and it will include the Yoshida lifts. So actually, for that will also reflect in the the normalization part in our the denominator in the end at the denominator that it will the denominator will include some Peterson norm on the of F and G on the quaternion algebra.
Thank you. Thank you.
Anybody else?
So do we assume that F has no other congruences with other modular form?
So for this part, no. But to go from this congruence ideal to bound the Selmer group, then we need to either assume that no congruence and or we need to handle that case.
You can do that instead of taking it for a family. You can take for a local component of the algebra, I suppose. What you explained.
Right. So yeah. So yeah, I can take a local component. Then it will kind of if I then that will exclude the yeah. If there's no residue, if there's no congruent, then I can exclude. If I assume that there's no congruence with the other, if F has no congruence with other modular forms and G has no congruence, then by Toko, then I can take local component. I can exclude those Yoshida leaves.
Okay, thank you.
Maybe I will ask some questions. All these Peterson inner products, Rayleigh's inner product formula, theta lifts are being done for complex field, or they are being done for some mod P situation?
Mod P situation. Do you mean like define it for?
This inner product formula.
Right, I have a Rayleigh's inner product formula, yes.
I mean, I know this is studied for complex representations.
Right.
A sense that they are somehow mod P valued or integral valued.
Okay, so this actually they are so here is a complex valued, and yeah, so yeah, when we compute it, we still take it to be a complex valued, but if we interpret as the interpolation by the element we constructed in this lambda 2, actually we already have the renormalization to get the value to be algebraic, but to really compute it, we still work with the complex valued Rayleigh's inner product formula.
But the Peterson inner product upon some L value is somehow integral valued, and that makes sense in a family.
I
mean,
right.
Eventually, you are doing all this for purpose of doing some mod P.
Right. So what we do is actually we also need to kind of we have the inner product formula, and we also need to properly normalize it. So in this case, we know the period will so the value will be the Rankin-Selberg L function for f and g at 1, and we know that we need to renormalize it. So we need to divide by the period, which is a Peterson norm of f to get it algebraic, and then we need to multiply. We need to multiply a congruence number associated to f to get its p-adically integral. So after this renormalization, then it will be we know that it will be a integral p-adic value and can vary in family.
All right, thank you. Thank you. So let's.
Thank you.